Hello and welcome to our Collaborative Research Center Transregio 270 Homage. Homage stands for Hysteresis Design of Magnetic Materials for Efficient Energy Conversion. My name is Oliver Gutfleisch. I'm a professor in material science at Technische University of Darmstadt and I'm the speaker of the center. The co-speaker is my colleague, Professor Michael Fahle from Physics at University of Duisburg Essen. The center has more associated partners at the University of Wuppertal and also at the Max Planck Institute of Ion Research in Düsseldorf, as well as the Ernst-Ruska Center in Jülich. Magnets are everywhere. Every single one of us uses magnets in their daily lives, dozens of them, knowing or not knowing. Very importantly, magnets are key components in energy technologies, for wind turbines, in electromobility, for transport applications, but also in automatization and robotics. Magnets are in many electronic audio communication devices, but also in many medical equipments. So now we face fundamental global challenges when developing all these high-tech technologies. We need, for making high-performance magnets, critical materials. These are strategic metals, most importantly, the group of the rare earth elements, the so-called lanthanides, but also elements like cobalt. We need a sustainable and ecological, feasible supply of these elements. Often overlooked in electromobility is that every battery needs a magnet. With more powerful magnets, we can extend the driving range of electric cars, for example. So with this rather complex image, we want to catch your imagination and we want to communicate our central ideas of homage. What we see is in red and blue a maximized and minimized hysteresis. They symbolize the project areas A, permanent magnets with large hysteresis, and project area B, magnetocaloric materials with minimized hysteresis. The colors red and blue also indicate that we are developing a solid state efficient heat pump. Red, hot, blue, cold. We also show in our hysteresis loop a third dimension. With this we indicate that we can use additional stimuli to manipulate the hysteresis of magnetic material. Stimuli like strain, pressure, ultrasonic manipulation. We can go further and try to understand the complex interplay of the different subsystems. We need to consider the magnetic, the electronic and the crystal lattice subsystem to fully understand hysteresis. We need to understand how they crosstalk to each other and need to disentangle them. Next, we can see within our hysteresis loops a complex microstructure. We try to understand microstructures on all length scales down to the atom or even to the electron. We can also see neural networks. That means we develop modern machine learning approaches in our center which help to enable an accelerated material discovery and also an accelerated data mining and analysis. The beauty and complexity of magnetism is visualized at the bottom of this figure by the magnetic domain structure. Lastly, but very importantly, we develop unconventional processing techniques, advanced synthesis like additive manufacturing, where we use electron beam or laser melting to locally manipulate magnetic properties, local hysteresis, and from this extend to a global, useful and technical relevant hysteretic property. To conclude my initial statement, I'm very happy and very proud to be able to coordinate with my colleague in Duisburg Essen this large collaborative research center. You will see in the following videos all the contributions of the different experts from many different fields, and we believe that we can make with these different contributions new magnets which operate close to their physical limit and which will enable these important new technologies for energy conversion and electromobility. Thank you very much.
Hi, I'm Lukas Schäfer and currently a PhD in the group of functional materials in the material science department at the Technische University Darmstadt, and I'm working on the project A01 within the CRC 270. I got into the world of material science and later functional magnetic materials, especially permanent magnets, because it unites the complete chain from the elements and their properties described by quantum mechanics up to the synthesis, processing and application of such materials in devices we use every day and of which we actually need more and more. Obviously, we strive to produce and use these materials more efficiently and in a more sustainable way, and therefore in Project A01, together with my supervisors Professor Oliver Gutfleisch and Dr. Konstantin Skokov, we are working on the further development of such neodymium-iron boron magnets, which are used in several applications due to their high magnetic performance. For such magnets, we observe a large gap between the theoretical and the attainable magnetic properties or performance, which is the so-called Brown paradox. This is caused by an incomplete understanding of how to create and effectively use desired micro and nanostructure features, and a lack of profound knowledge about the demagnetization processes occurring at the nanoscale, at grain boundaries or other defects. In Project A01, we will address both topics and by this try to develop strategies to challenge the Brown paradox.
Hello, my name is Georgia Kuzia. I'm a PhD candidate at the Department of Material Science at the Technical University of Darmstadt. I'm working for the group Advanced Thin Film Technology, and in this group we are growing thin films. I'm working with ultra-high vacuum techniques and more specific with molecular beam epitaxy. In the SFP 270, I'm working for the project A02, and I'm growing samarium cobalt thin films. Samarium cobalt is one of the most known permanent magnetic materials. We grow this material in the form of thin film in order to understand the hysteresis mechanism. Going really in nanoscale, we have the opportunity to study the material and understand what is happening in the atomic level. Molecular beam epitaxy gives epitaxial thin films, and this also gives us the opportunity to have atomic layer by atomic layer and study the interactions. This will give us then the understanding for hysteresis mechanism and apply for bulk magnetic materials. Our molecular beam epitaxy is equipped with reflection high energy electron diffraction. So during the growth of the thin film, we can know if we have an epitaxial, polycrystalline or amorphous thin film. In the CRC TRR 270, we have the opportunity to collaborate with different universities like the University of Duisburg. This gives us the opportunity to understand and study better our films, our materials, and also collaborate with different people.
Did you know that X-rays are not only used to image broken bones? Scientists also use it to learn about complex materials. My name is Demir Günzing from the Experimental Physics Group of Heiko Wende at the University of Duisburg Essen. Within our project, we utilize different X-ray based techniques to characterize permanent magnetic materials. For example, here in our lab, we conduct Mössbauer spectroscopy measurements. With the help of decaying atoms, we can see the environment of iron and tin and learn about these magnetic materials. We are visiting facilities all around the world to conduct our studies. These facilities, or synchrotrons, have enormous tubes, often more than 100 meters long, where electrons travel in circles. The acceleration creates photons with high energies. We use these energy photons, or X-rays, to probe excitations in the measured materials. Let me show you an example. You can see here a 3D magnetic image of a permanent magnet, neodymium iron boron. Here we use a special 3D magnetic imaging technique to decipher the structure in all spatial directions. The most exciting aspect of this project is its collaborative nature. Our project relies on many different scientific disciplines, as well as collaborating with large-scale facilities. I find it personally fulfilling to contribute to this effort, searching for new and efficient magnetic materials.
Hi, I'm Nicolas, a PhD student in the CRC 270 Homage. My project is A04, Shell Ferromagnetic Materials, tuning the magnetic hysteresis by nanoscale selective phase decomposition. The goal is to optimize the properties of permanent magnets. This can either be done by increasing the total magnetization, so to say the strength of the magnet, or by increasing the corrosivity, which is the resilience of the magnet against external magnetic fields. The samples investigated in my project, for example, have a surprisingly large corrosivity. Magnets can be found everywhere in our modern world. From hard drives to electric motors, there are many possible applications. Some may not even be discovered yet. In my project, I investigate the magnetic properties of manganese-based magnetic alloys. Here, the meticulous sample preparation and treatment is responsible for the intriguing magnetic properties. It all begins with melting pure elements in an arc melter. An electric arc between a tungsten needle and a water-cooled copper crucible can easily reach temperatures above 2000 degrees C. Then, after a detailed structural characterization, we can investigate the magnetic properties. This is done in a superconducting quantum interference device, in short, SQUID. It can measure the magnetic field-dependent magnetization of a sample in fields up to 5 Tesla. The data is then analyzed, and the results are used to optimize the material composition and treatment further. The final goal is a new generation of permanent magnets with a preferably small ecological footprint.
My name is Timlane Oyedeji. I'm working on project A06, phase field modeling of microstructure evolution and properties of magnetic materials using laser powder bed fusion. I'm working with the group of Professor Xu and also with Yang Wei Yang. So additive manufacturing involves the building up of an object using layer by layer deposition of materials. Laser additive manufacturing involves the use of laser to melt and solidify materials in the powder bed. The final properties of material that you get, for example, the magnetic hysteresis, is dependent on the microstructure, which also is dependent on the process parameters. So in my project A06, what we try to do is to understand how to use laser additive manufacturing to influence the magnetic properties of a material by influencing the microstructure. In laser additive manufacturing, the physical processes that you have are different and interactive, but they also occur at different length and time scale. For example, on the macro scale, where people care most about the finer geometry, on the mesoscale, for example, you have processes such as melt flow, solidification, grain growth, and on the microstructure features at this scale, you have features such as porosity, and due to high temperature gradients, sometimes you can also have thermal shock, which leads to crack. On the micro scale, on the other hand, you realize that your grains are not fully dense. It's possible for you to have dendritic structure, and also it is possible for you to have segregation of solutes or nanoparticles in the grains or grain boundaries, which can also influence the magnetic properties of a material. So in project A06, what we do is we try to build up a multi-physics, multi-scale modeling and simulation of laser additive manufacturing, and we also collaborate with our colleagues for characterization experiments. For our workflow, what we do is first we have laser powder bed process simulations where we take into account processing parameters and material properties. Accompanied by this simulation is thermoelastoplastose simulations where we obtain the residual stresses on the plastic strain, as these effects are related to the final magnetic properties of a material. Also, we have solid-state phase transition, for example, for specific materials, for example, iron nickel, where you have gamma to gamma dash phase transition. Lastly, we also conduct micromagnetic simulations where we obtain magnetic hysteresis at each point in our sample, and we take an average of these hysteresis as the average hysteresis of our sample. Lastly, I show you a simulation example of what we do, where I show a multi-layer build-up of an iron-based alloy, where you have the layer build-up of the materials and also the movement of the laser beam. On one side, I also show the build-up of the plastic strain and also the build-up of the residual stress during this layer-by-layer build-up. Thank you.
I'm Maximilian Reichel, the PhD student of the project AO7, Scale Bridging of Magnetomechanical Mesostructures of Additive, Manufactured and Severe Plastically Deformed Materials. The goal of the project AO7 is to give simulation-based recommendations to enhance the magnetic properties formed by novel processing routes. Therefore, FEM-based analysis of micromagnetic mechanically coupled simulations are applied. The implementation of such an FE framework follows the fixed procedure, starting with the field equations that are the magnetic Gauss law, the Gilbert equation, and the balance of momentum. Those three equations are transferred into their corresponding weak forms using a variational approach. These weak forms can now be utilized to derive a system of equations that is solved using an iterative Newton-like method. The definition of a boundary value problem in the simulation framework starts with the geometry, like the SEM image of a given neodymium iron boron microstructure. To perform simulations, this microstructure needs to be transferred into a discrete counterpart. Together with the beforehand introduced system of equations and the discrete microstructure, the following simulation results can now be obtained. What is possible in 2 dimensions is also possible in 3 dimensions. As shown here, the simulation results of the magnetization reversal of an artificially generated polycrystalline microstructure or the hysteresis simulation of this nanodot. As mentioned before, the goal is to predict the behavior of magnets formed by novel processing routes, like the simulation results of a microstructure formed by rotary swaging, as shown on the right, and to give recommendations for improvements.
Hi, I'm Franziska Stab and I'm the PhD student of project AO8 and I'm working in the group of Professor Carsten Durst, the physical metallurgy, on magnetic hardening by severe plastic deformation processes. In this project, we develop a new process route for the production of hard magnetic materials and therefore we are using the high pressure torsion which we apply to powders. During the process, we apply a pressure between 2 anvils of up to 200 tons and then simultaneously one of the anvil is rotating. And this induces a very large torsional shear strain and this leads on one hand side to the consolidation of the powder and on the other hand side to a grain refinement and an increase of the dislocation density and grain boundaries. And these effects are well known to affect the magnetic properties such as the coercivity. By using powder plants as precursors, we can go beyond the limitation of conventional production routes, since we are not limited here to phase diagrams. So by the choice of the initial powders, we can vary the intrinsic magnetic properties. And by the process parameters during the high pressure torsion process, we can tailor the microstructure and adjust the extrinsic properties and can maximize the magnetic hardening effects. So in the end, we can generate bulk composite materials with grain sizes in the nanometer range. And recently, the process was very successfully used for the production of samarium cobalt-5 copper nanocomposites, which have promising magnetic properties. So by the aid of this process, we learn to understand the role of different microstructural features, which can then be used as guidelines for the development of a continuous severe plastic deformation process, such as the rotary swedging, which is used in project AO9. Within my project, a new high-pressure torsion press was acquired, which can work at temperatures of up to 800 degrees C under inert gas atmosphere. And now with this new press, I'm very excited that we can process also oxygen-sensitive materials, such as the rare earth-containing hard magnetic phases, and we can do the process at elevated temperatures, leading to even higher possible deformations. I'm very happy to have the chance within the framework of the SFB to be able to work on magnetic materials in such a big community and to be part of this team here. The materials are used in so many technologies which are relevant for our all future, and I'm really excited about doing research on such an important topic.
My name is David Löffler and I work at the Mechanical Engineering Institute for Production Engineering and Forming Machines as a PhD student. Within the CRC 270, I'm working on the project A09, which deals with the processing of hard magnetic materials using forming machines. In this project, we use the process of rotary swagging to process magnetic materials. The process is characterized by high productivity, which is an advantage over conventional processes for permanent magnet production, such as sintering. So far, continuous manufacturing processes are not yet available for magnet production, which leads to high energy consumption during manufacturing. In addition, to improve the production technology, the aim of this project is to design the microstructure of the magnets by forming metal matrix composites. In addition to improve the production technology, the aim of this project is to design the microstructure of the magnet by forming metal matrix composites. Microstructure influences important magnetic parameters such as coercivity, thus the resistance of the magnet to the magnetic reversal. These properties are important in order to be able to manufacture high performance and applications such as electric motors and generators. These play an important role in achieving a turnaround in energy policy and ecological traffic turn. Metal matrix composites consist of a matrix and at least one other different magnetic material embedded into the matrix. The process is started with the reduction of the rod consisting of a core of hard magnetic material and surrounding tube of the grain boundary phase. After the reduction of the diameter of the rod, it's again bundled and afterwards reduced in diameter. This accumulated process makes it possible to produce a desired microstructure. This procedure is known from the production of Damascus steel. Since magnets are used in an incredible variety of applications, I'm fascinated by the topic and the project and hope that the results obtained by the CRC will contribute to fight against the climate crisis.
Hello, my name is Jianing Liu. I'm working as a doctoral researcher in the group Functional Materials, leading by Professor Oliver Gutfleisch at Technische University Darmstadt. Within CRC 270 Homage, I'm working on the project A10. It is focused on additive manufacturing of permanent magnets, which may synthesize the bulk permanent magnet from powder layer by layer. As you may know, reaching net zero by 2050 is one of the most challenging topics for humans ever. Permanent magnets are key components for energy technologies, such as e-mobility, robotics, and so on, which provide solutions that contribute to the journey towards net zero. And additive manufacturing could be an attractive method for manufacturing permanent magnets, as it minimizes the use and waste of critical and supply-limited materials, and it also enables the printing of complex geometries. Furthermore, printing layer by layer enables to print the magnets with gradient properties. This will largely extend the application fields of permanent magnets. I'm really excited on the project because I'm working on an advanced industrial technology which could contribute to a modern, high-efficient, and low-emission world.
My name is Dr. Anna Zifus. I'm Junior Research Group Leader at the Universität Duisburg Essen, where I'm involved in the sub-project A11 since March 2021. Our main goal is the nanofunctionalization of magnetic micropowder for engineering grain boundaries during additive manufacturing to build magnets with maximized hysteresis. It is hard to imagine the 20th century without permanent magnets, right? However, they are mostly based on rare earth elements, so their supply and their availability represent critical factors and novel technologies that minimize the use of such rare elements in permanent magnets needs to be developed immediately. Here, additive manufacturing is a promising approach as it allows the production of complex structures under low waste conditions, minimizing the need for rare earth elements. Printing permanent magnets, however, is challenging as melting and solidification critically affect the macroscopic and microscopic properties of permanent magnets. A11 addresses exactly this issue and adds nanoparticles to the surface of the magnetic micropowder to sufficiently influence even the melting and solidification behavior. We produce our nanoparticles surfactant-free in water using high-power, ultra-short pulse laser systems. By mixing the resulting colloid with the permanent magnetic micropowder and subsequent drying, we obtain our nano-additivated powder that we investigate extensively in suction casting, a process that mimics kind of the powder bed fusion, but also in real powder bed fusion applications. We found that printing of the magnetic powder that contains just 1 weight % nanoparticles leads to as-built parts showing a drastic increase of the permanent magnetic properties, which is already great. We, here in A11, address the complete process chain, starting from the nanoparticle synthesis to the analysis of the final product, including in-depth magnetic, chemical, and microstructural characterization within the TRR 270 infrastructure. In the second funding period, we want to shift our focus to the powder bed fusion process using our knowledge on nanomaterials, powder loading, and oxygen tolerance from the first phase to print permanent magnets under variation of the volumetric energy density applied during printing. Particularly interesting is then the in situ observation of the nanoparticles during printing using optical emission spectroscopy.
Hello, my name is Bendik Beckmann and I'm the PhD student working on project BO1 of the CRC 270 in the Functional Materials Research Group led by Professor Oliver Gutfleisch here at the Technical University of Darmstadt. My project specializes in functional magnetocaloric materials, which are materials that can be used for cooling, as they change their temperature upon application of an external magnetic field. In our age, climate change, population growth and the transition towards renewable energies represent 3 of the most urgent worldwide existential challenges, demanding energy efficient and environmentally friendly future technologies. These current developments lead to an ever-growing demand for cooling, which is predicted to exceed the energy consumption for heating this century. Thereby, we live in a cryogenic age, which becomes apparent when we think about the role of cooling in our everyday life, including our fridges and air conditioning units at home, the global food supply chain, as well as server rooms and medicine requiring to be cooled. In this regard, magnetocaloric cooling is of importance as it represents a more energy efficient and environmentally friendly future cooling technology compared to the nowadays widely used vapor compression refrigeration cycle. And this will become even more important in the future with respect to the liquefaction of hydrogen, which is an alternative energy carrier and key enabler in the successful transition towards renewable energies. I'm excited to work for this project as I'm able to work on solutions for the most pressing issues of today by improving energy efficiency and reducing environmental impact through technological progress.
Hello, I'm Ivan. To put it simply, I'm a person who brings materials into existence. In other words, I'm creator, not that creator who manages all affairs, but nevertheless, I can assure I'm responsible for creating some small boards. How small, you ask? Something like 50 nanometers thick. And what are these like, you ask? They're like films, or better to say, thin films or layers, thin films of Mach phases. Did you hear before Mach phases? They are inherently beautiful substances made up of carbon and other chemical elements like chromium and gallium. It's important to have at least 3, but many others are possible. So their beauty is an alternative one you cannot find in nature easily. The layer of carbon alternates with a layer of chromium, then layer of gallium comes, and this repeats until nature allows. Or I can also stop such an intimate process just by terminating a sequence of pulsed laser deposition. So not only this beauty makes them so special. People even got together and launched a scientific project. You could call them two-faced. One may resist a harsh environment as a ceramics and be conductive metal too. But that's not enough. We are struggling to make them magnetic, to bring such resistant materials for the need of the magnetic refrigeration. It sounds cool, doesn't it? We're trying to produce a substance which never existed before, and some clever theoretician predicted a new life for it. And this substance might be used for many years in refrigerator, and doesn't matter, no matter how harsh environment, isn't it? It's always like that. So the beautiful things, beautiful ideas are hardest to put in life. This inspires me a lot. To produce a magnetic caloric Mach phase is a quite challenging task, but dealing with the Mach phases of thin films allows us to be more flexible in the way of stabilizing them. Synthesis of thin films is far from so-called equilibrium, and one knows very well when conditions are far from balance, then more opportunities appear. And we are working on this project to use such opportunities to acquire new knowledge on unexplored Mach materials. And what for? To contribute with this to a greener future for our planet.
Hello, my name is David and I work at the Structure Research Group of the Material Science Department at the TU Darmstadt. Within the CRC homage, we are investigating magnetocaloric materials which have promising properties for energy-efficient cooling. The material I'm mostly investigating is composed out of nickel, cobalt, manganese and titanium, and depending on temperature and magnetic field, this material can have different structures. If we cool the left structure at some point, it transforms to the right structure, and if we heat it up again, it transforms back. This process can also be triggered using a magnetic field, which leads to the cooling effect we want to have for refrigeration. Using X-rays, we are investigating how the phase transition takes place and what the exact structures of the high temperature and of the low temperature phases are, and how these structures interact with the characteristics of the phase transition. We are aiming for a better understanding of the phase transition and want to improve the material and to find new materials which also undergo such phase transitions and are suitable for magnetocaloric applications. We are doing this in our home laboratory and also at large-scale facilities like the ESRF in Grenoble. A very important and enjoyable part of my work here is also the collaborations with many projects within the CRC. Working with many people in new research fields is always exciting.
My name is Olga Miroshkina and I'm a postdoc at B06 project called Rational Design of Narrow Hysteresis Materials by Tailoring Magnetoelastic Interaction. This is a theoretical project which aims to identify the complete set of relevant microscopic mechanisms which links to a different degrees of freedom in magnetocaloric materials. Why is this important? All the work on the multifunctional materials, and these materials have a unique combination of different characteristics which allow them to demonstrate a variety of functional properties and to transform one type of energy into another. Of course, finding of such materials is a challenging task. And theoretical modeling is extremely helpful here because it allows comparatively fast and technically less complicated, in comparison with experiment, get an information about the material. With the development of high-performance computers, modeling is becoming more important. Assuming the knowledge of type of atoms that make up the material, computer modeling allows us to answer the questions: what is the atomic structure of material, what are its properties, and how we can change the composition or interactions between the atoms so that the new material has the desired properties. In order to answer these questions, many methods have been developed, and all of them can be divided into two classes: first principles methods, or ab initio methods, and empirical methods. Empirical methods uses a constant obtained from the experiment, while our main focus is the first principles methods, which are based on the quantum mechanics and statistical physics and do not use any experimental data as an input. The only information in such calculations is knowledge of the atomic number and the atomic weight of the atoms that make up the material. So one of the first principles method is density function theory, abbreviated as DFT. With DFT, we work at the nanoscale, and the results obtained here can then be used as an input for other methods. The idea of DFT is to express the total energy of a many electron system in terms of total electron density rather than wave function. It allows to decrease significantly the computational cost of calculations and to get reasonable results using appropriate approximations. So, and what can we get from this method, from these calculations? DFT provides total energy, magnetic properties, electronic and vibrational densities of state as a function of microscopic state variables such as magnetization, volume, and strain. Having this calculated, we can analyze the characteristic of the material, distinguish the mechanisms responsible for certain properties, and maximize them. I suppose that everyone in this project is concerned with the question of how to bring the new, effective and cheap multifunctional materials closer to the production, so that they are available to mass consumers and can meet humanity's growth need of cooling devices. And in the framework of CRC TR 270, all the participants work as a small cogs in the big machine, the joint efforts of which help to bring the future closer to the present.
Hi, I am Ali. I am a PhD student at TU Darmstadt, and I'm a part of project B07 of our CRC, and I'm working on magnetic max phases. So what are the max phases? So max phases, they are compounds of a transition metal, carbon, and a group A element. And what's so interesting about them? Well, they are compositionally diverse and they have layered structures. This gives them unique properties, which are a combination of both metal and ceramic-like properties. But what not known so much in these materials is magnetic properties. This is what we try to understand and investigate, why magnetic max phases are limited in number, even though they are promising, they could be promising for magnetic applications. Okay. And at the end of this project, our main goal is to find out new magnetic max phases that are suitable for magnetocaloric applications. How do we achieve this goal? Well, we do simulations. We ask computer to do the work in this. So we do quantum mechanical simulations. In these simulations, electron density is a central quantity, and many body interactions, that is meaning the interactions of electrons and ions, they are complex and they are simplified in such simulations so that quantum mechanical equations, they can be solved numerically in a high-performance computer within a reasonable time. This theory is what is termed as density functional theory, and with this theory we can I calculate magnetic, thermodynamic, and electronic properties at 0 Kelvin temperature. And this These properties are then verified or studied by our experimental collaborators and co-workers within our CRC, and this way we work in a strong collaborative environment within our CRC. So what excites me most about this project is that we can collaborate with our experimental co-workers and can really compare theory and simulation. This way we can verify whether theory and experiments, they agree with each other, and we can compare the results at the end. And at the end of this project, our main goal is to find new phases, both experimentally and theoretically, that can help in improving the properties and applications that can find applications in magnetocalorics.
Hello, my name is Ina Khairani and I came from Indonesia. I moved to Wuppertal at the end of 2020 to work as a researcher for Professor Spila's group at the University of Wuppertal. Here, my main task is to increase the production of nanoparticles in the laser ablation in liquid. Laser ablation in liquid is a simple process to produce nanoparticles. It requires a laser with high enough power, liquid which can be as simple as water, and a target material. The target material can be anything, but commonly it is metal or alloy in a bulk or pressed powder form. The produced nanoparticle can be used in many different fields, such as for additives to make scratch-resistant films, sunscreen, and strengthened steels. They can also be used as catalysts to accelerate a process and used as a contrast agent in MRI analysis. In the future, nanoparticles may be used for hypothermia and targeted drug delivery to cure cancer. And in this project, my colleague Shabir is using nanoparticles to make ink for the lasered sintered magnetocaloric lines, which he will also explain later. So to keep up with this demand for nanoparticles, we need to increase the production rate of the nanoparticles in the laser ablation in liquid. So that is why the goal to scale up the production rate of nanoparticles is very important.
Hi, my name is Shabir Tahir and I am originally from Pakistan. I am a PhD researcher in Professor Bilal Goikce's group at the University of Wuppertal in Germany. I am currently working on the synthesis and sintering of magnetocaloric nanoparticles using lasers. What I do is I use picosecond pulse laser to ablate magnetocaloric compositionally complex alloy to generate nanoparticles. And these alloys are composed of multiple elements. And what I get is, after the ablation, is also multiple elemental composition within the nanoparticles itself. The generated nanoparticles are first used to produce nanoparticle ink, which is then dispersed on the glass substrate and sintered using continuous wave laser. The direct writing employing continuous wave laser can be used to produce 2D magnetocaloric custom structures with micrometric resolution. Additionally, these magnetocaloric nanoparticles can be used to generate 3D structures using, for example, laser powder bed fusion process where layer by layer metal powders can be printed. In terms of the applicability, they can be used to design microcoolers for heat extraction from devices such as compact high-performance laptops, smartwatches, minuscule sensors where heat extraction is really difficult due to their compact size. The thing that excites me most is the laser processing itself, that how tuning the laser processing for a wide range of materials would change the material properties and could lead to achieve the best magnetic and magnetocaloric properties. Thank you.
Hello, my name is Nikita Polin and I'm a PhD student from the Max Planck Institute for Eisenforschung in Düsseldorf. In my PhD project, I investigate magnets, and I do this with the technique called atom probe tomography. This is basically a fancy three-dimensional microscope which makes three-dimensional image of individual atoms. What is it good for? Well, from the knowledge of the atomic positions, we can make suggestions how to improve our magnets. And this works in the following way. Imagine this is a magnet which is worse than we expected, and we want to know why. So what I do is I zoom inside of this magnet, until I see things which are 1,000 times smaller than a human hair. And what I would see is, in the end, something like this. A bunch of atoms connected to each other in a regular way. We also call it atomic structure. And here you see also two species, green ones and uncolored ones. And now, if I exactly know where all the atoms sit, I can say things like, well, it's not a surprise this is a bad magnet. The arrangement of the atoms is not perfect. For example, the green ones, they should be a plane and not a line, like it's here. So next time, we should fabricate our atom better in a different way. So from the knowledge of the atomic arrangement, I can deduce how to improve a magnet. And having better magnets, we can put them in electric cars, in wind turbines, and thereby contribute to a more sustainable future. Now, how does the atom probe work? It works as follows. I cut out a small piece of my magnet, which is 1,000 times thinner than a human hair. I put this inside the atom probe and I shoot with a laser on top. And what happens is that atom by atoms, they are detached and fly away. First atom, second atom, and so on. I catch the atoms on the detector and calculate back where the atoms came from. And if I do this for all the atoms, I in the end have a three-dimensional image where I know the species, colored or green ones. And the cool thing about this is that I have a three-dimensional image when two normal microscopes give only two-dimensional image, so they look only from one side. And of course you're losing some information. With 3D images, you know more. And here is an example of an animated 3D image that I have acquired during my PhD. You see that regular green and blue planes are forming, and they are quite important for the magnetism. And as industry wanted to know, why is the magnet worse than we expected? And with the help of the atom probe, we could answer this question. The problem was inside these blue and green planes, that they had just not as good composition as we wanted it to be. Now I hope you know what the atom probe is, a fancy 3D microscope for atoms, and I hope you know why we perform atom probe on magnets. So the knowledge from atom probe is key for their improvement.
Hi, I'm Nicolas and responsible for the magnetic roller coaster, which is a demonstrator of the CRC 270 homage. The idea behind the demonstrator is to bring scientific ideas and concepts closer to the general public. They have to be educational and exciting at the same time. We built a magnetic roller coaster using strong permanent magnets as the track and a Type II superconductor as the car. When the superconductor is cooled below its critical temperature, the pinned magnetic flux locks it in a predefined height above the magnets. We are using IBCO, yttrium barium copper oxide superconductors, which have a critical temperature of about 90 Kelvin. This means liquid nitrogen is sufficient for cooling. In the superconducting state, the car is levitating above the track, and friction is greatly reduced. It can even defy gravity, drive sideways or even upside down. A crucial part of this demonstrator is the magnetic track. Here we used neodymium magnets, which are the strongest commercially available magnets. One of our collaborative research center's main goals is the development of new types of permanent magnets. These are necessary for many technological applications, among other things, more efficient energy conversion.